Hello, my name is Martin Pike and welcome to this lecture from the Ada University course on Mixed Language Programming with Ada and C. The subject of this lecture are the features of the Ada programming language that provides support for integration with the C programming language. Together we shall complete a series of slides and then you will be assessed on your learning using some quiz questions. The Ada programming language offers unique features for interfacing to foreign programming languages that are part of a mature and progressive ISO standard 8652 revision 2012. If you haven't started at the beginning of this lecture series, I would strongly suggest that you stop watching this lecture and attend the first lecture in this series. It contains significant background information that will greatly help with learning this subject. From this point onwards, it is assumed you understand the Ada aspects involved in Ada and C mixed language programming. To recap, they are convention, import, export, link name, and external name. In this lecture, we're going to cover how these aspects are applied to mixing Ada and C. We're also going to cover the interfaces child packages specific to mixing Ada and C. Finally, we'll look at how you can have a main program in either language and make use of foreign language subprograms. We start off by looking at how a subprogram implemented in C can be imported into an Ada main program. The example code shows an Ada main program declaring a nested subprogram that is an imported function using the C calling convention. The external name aspect has been used to identify the name of the subprogram in the C source code. The subsequent fragment of C code shows the subprogram implementation that returns the numeric value 10. The body code of the Ada main program calls the imported C function using the Ada entity identifier, which causes the value 10 to be output. It is also possible to import memory objects from C, as we can see in this fragment of Ada code. The familiar convention, import, and external name aspects are used to specify the Ada entity used to identify the foreign language memory object. In this case, the memory object is called the length, and it is defined in the subsequent snippet of C code as being a constant size_t typed value of 20. You will notice the use of an Ada type from interfaces.c that resembles the C size_t type from the standard lib header file. We will come on to the details of interfaces.c later in this lecture, but for now understand its vital role in this subject. The output from the Ada main program would be the value 20. Exporting an Ada subprogram to a C main program is just as simple as importing a C subprogram into Ada. The exported subprogram entity looks very similar to an imported subprogram, with the only difference being a swapping of the import aspect to the export aspect. Of course, there is a need for an implementation of the exported subprogram in Ada. Here we show a package specification containing the declaration of an exported subprogram, and notably the Ada entity name is different from the name used to reference it externally. There is a simple implementation in the associated package body that returns the value 60. The example C main program here calls this exported Ada subprogram to print out the value. In this example, we export an Ada entity to C that's a constant memory object with the value 80. The same aspects have been used as when exporting a subprogram, but the external name aspect has been altered in this case to the length. On the C side of the program, the main function again has to call ada init and ada final, and then can make use of the exported ada entity. The output from this particular C main program would be the value 80. The package interfaces.c contains the basic types, constants, and subprograms that allow an ada program to pass scalars and strings to C functions. The minimum number of types, constants, and subprograms are provided to enable interfacing to C foreign language entities. The reader is encouraged to study the contents of this package in detail offline from the course, as its contents are very valuable to a programmer. Interfaces.c is the parent package of two important child packages related specifically to C pointers and strings, two areas where C and ada differ considerably. It is also possible to import arrays of memory objects from C into ada. In this example, we see a piece of C code that declares 4 size T typed memory objects in an array. This array is then imported into an ada entity that has been typed using an ada array declaration. The ada main program iterates over the array, printing out the hex version of the C memory object. In this particular case, the hex values 10, 20, 30 and 40 are output to the console. The interfaces.c.strings package is defined in the Ada Programming Language Reference Manual as a package declaring types and subprograms, allowing an Ada program to allocate, reference, update, and free C-style strings. In this example, we see a snippet of C code declaring a function that returns a pointer to the string Hello World. The Ada main program imports the C function as an Ada entity called getString. The Ada main program then goes on to use features of the interfaces.c.strings package to convert the string pointer into a suitable Ada access type, and subsequently accesses the target object as an Ada string. The Ada string is then suitable for input into the ada.textio putline subprogram, which will produce the program's output of the string Hello World. Exporting Ada strings to C main programs can be made simpler by using the interfaces.c.strings package. In this code example, we see a set of constant Ada strings being declared using types from interfaces.c.strings. The data structure is exported using the C convention as the externally named entity sum_strings. The C main program is able to access the array of strings and iterate through them, printing them out until it finds a null pointer. Please note the use of the null_ptr constant from interfaces.c.strings. The child generic package interfaces.c.pointers allows the Ada programmer to perform C-style operations on pointers. It includes an access type pointer that is C compatible and corresponds to one use of C's element star. The generic allows two styles of usage, one in which the array is terminated by a special terminating element, and the other in which the programmer needs to keep track of the length. This is achieved by providing two versions of a function called value that dereferences a pointer and delivers the designated array, one provided with the terminator and the other with a length. The package also provides several pointer arithmetic functions and copy procedures that copy the contents of a source pointer into the array designated by a destination pointer. If generics are new to you, then I would suggest you visit the Programming in the Large course from the Ada University, where they are covered by a dedicated lecture. Ada can also import C function pointers and use them as access to subprogram entities. The C code declares a function called C_function that accepts a pointer to a size_t object that is eventually dereferenced as an input to printf. The function pointer is assigned to the address of this C_function. The Ada main program declares an access to subprogram type that matches the signature of the C function pointer. It then imports the func entity from C and dereferences the pointer to invoke the C function that eventually outputs 10 using printf. In this slide, we are going to deal with an issue that may arise when using a C main program and exported Ada entities that require elaboration. The example code snippet shows an Ada package specification exporting a memory object that is explicitly initialized with the result of calling the function f. The explicit initialization is performed by the Ada elaboration code, and this must be executed by the C main program before attempting to access the exported entities. The C main program must call an external function called AdaInit to execute the Ada elaboration code, and if this was omitted, the C main program would display a random value, almost certainly not 55. The C main program must also call the external function AdaFinal upon completion to ensure all Ada finalization code is also executed. The GNAT tools contain a very useful feature for automatically generating import pragmas for entities defined in C header files. The example header file here, called clib.h, provides 3 function prototypes with various return types and parameters. It is possible to produce an Ada specification for this C header file by passing a particular flag to the GCC compiler. The -fdump Ada spec flag is passed to GCC along with the name of the C header file. The "C" flag is used to ensure comments from the C header file are copied into the generated Ada package specification. The resulting Ada package specification for the example C header file is shown at the bottom of this slide. Each function has been imported as an Ada entity, and appropriate data types have been used for return values and parameters. Note the use of interfaces.c.strings for the character pointer return value from function 3. At time of writing, Ada 2005 pragmas are generated, but these could be manually converted to Ada 2012 aspects. Perhaps in the future, support for Ada 2012 aspects will be added. We've now reached the end of the slides section of this lecture. You should now have enough knowledge of this subject to complete a small quiz with questions designed to test your understanding. Each question is marked, and you will have a chance to review your score at the end of the lecture. Good luck! Question 1 kicks off with an example of importing a C subprogram into an Ada main program. The Ada entity get_length is a function represented by convention, import, and external name aspects. The Ada main program body calls getLength. If you think this code is correct, then please click the tick icon. Otherwise, click the line of code that is incorrect. The answer is no. The code is incorrect and will fail to link into an executable. The external name string must match the foreign language entity name exactly, including the use of the correct case. Here we used the camel case string getLength in the declaration of the Ada entity for the imported C subprogram. However, the C code used all lowercase for the declaration of the getLength function. Question 2 covers exporting an Ada subprogram for use by a C main program. The function get_length will return the value 60 when called. Study this code carefully. If you think this code is correct, then please click the tick icon. Otherwise, click the area of the code that is incorrect. The answer is no. The code is incorrect and will fail to execute correctly. There must be a call to Ada init before the use of any exported Ada entities by the C main program. Question 3 demonstrates the use of an imported memory object using the C convention. The program declares an Ada entity using the name the_length, but specifies a different external name for the entity in the foreign language. The foreign language has declared the memory object as a constant value 20. If you think this code is correct, then please click the tick icon. Otherwise, click the line of code that is incorrect. The answer is yes. The code is correct. Ada is able to use memory objects imported from foreign languages without having the responsibility for setting their values. Question 4 mixes the use of Ada access types with C pointers, but without using any pointer arithmetic. When the C program executes, it intends to output the number 50. The example code is much larger than previous questions, so please take your time to read it through and understand it. If you think the code is correct, then please click the tick icon. Otherwise, click the line of code that is incorrect. The answer is yes. The code is correct. It is perfectly safe to mix Ada access types with C pointers as long as the types from interfaces.c are used as the target types. Question 5 presents a method of accessing an array of C constants imported as an Ada entity. The body of the Ada main program iterates over the imported entity until the value 9999 is encountered. Again, this code is quite advanced, so please take some time to review it before attempting the question of correctness. If you think this code is correct, then please click the tick icon, otherwise click the line of code that is incorrect. The answer is yes. The code is correct, but it is not recommended to do this kind of access type manipulation. There are some big assumptions being made by the code in the question slide about the imported C data structure. A better solution is shown here. It is restricted to a single use of the tick access attribute and is made type safe by using the structure returned by the value subprogram from the interfaces.c.pointer package. It is probably debatable about which solution is better, but in the interests of fairness, both have been presented in this lecture. Question 6 is a multiple choice question, and it poses the question, which of these packages is not part of the hierarchy of packages rooted in interfaces.c? Please select your chosen answer and then click Submit to see if you are correct. The answer was interfaces.c.subprograms. This is not part of the interfaces.c package hierarchy. Question 7 asks what output will this Ada main program produce by using an imported C string. Will it fail to compile, output the hello world string, or raise a program error exception at runtime? Make your selection and click Submit to see if you are correct. The answer is the hello world string. As you can see, it's very easy to use C strings imported into Ada main programs. Moving on to question 8, we see an Ada package specification exporting a constant string using the C convention, and the external name is Ada string. The C main program uses an externally declared string entity called Ada string in a call to printf. Will the C main program fail to compile, enter an infinite loop and never return, or print the hello world string? Make your selection and then click the Submit button to check your answer. The answer was the hello world string. Again, this demonstrates how easy it is to use strongly typed Ada string declarations in a C main program. With this example, you can see that declaring all your C strings within Ada packages helps introduce type-safe data structures into your C programs. The penultimate question again asks to identify what string output an Ada main program will produce. Here we use data types from interfaces.c.strings to work with imported C functions that use char star entities. Interfaces.c.strings provides various type-safe subprograms for working with C strings. What do you think the output from this Ada program will be? Will it be the hello world string, nothing due to a program error exception at runtime, or will the code fail to compile in the first place? Select your answer and click the Submit button to see if you are correct. The answer is the hello world string. First, the char access array object returned by the imported C function is given to the toChars pointer subprogram from interfaces.c.strings. The result of this subprogram is given to value from interfaces.c.string, which will return an Ada string version of the character pointer. This is then permissible to be passed to the putLine operation from ada.text.io. Our final question continues the theme of using interfaces.c.strings. This code declares a constant set of Ada strings and exports them as the C convention entity called sumstrings. The C main program uses these strings in a loop. What do you think the output from the C main program will be? Will it be gibberish code, or the Ada code raises a constraint error exception at runtime, or the hello world string? Select your answer and click the Submit button to see if you are correct. Not surprisingly, the answer was the hello world string. You could use this type of constant Ada structure to limit the need for error-prone C strings and gain the type safety of Ada strings. That concludes the quiz. Please click the Continue button to review your score. Congratulations, you have completed this lecture. I hope you have found it a valuable step in learning the Ada programming language, and that you continue on to the other lectures in this course from the Ada University. Thank you.